Okay, so what we're going to do here is really suffer through a very long slide with 74 animations, having our first in-depth look at crystal field stabilization energy. And essentially the idea is, in a regular spherically surrounded atom, all of the d orbitals are going to be degenerate with this energy. However, when you get specific with that electrostatic field, and instead of it being spherical, you focus in the ligands in an octahedral environment, you get 3 orbitals are stabilized by minus 0.4 of the octahedral splitting, and 2 of the orbitals are destabilized by 0.6 of the octahedral splitting. Okay, and this is just as a result of the ligands are directly in touch with these orbitals. However, the ligands are kind of in between these orbitals, or these orbitals are in between the ligands. So you get stabilization down here, a destabilization up there. Now let's generate a little table here in which we're just going to go through every single possible interesting configuration. So I'll start with D1. Put an electron in D1 and it's going to go in the T2G orbital, one of these 3 triply degenerate, more stabilized orbitals. Okay, so we're going to define its electron configuration 1 in the T2G. Now you compare that to the situation in the barycenter, right, in which all 5 of the orbitals are degenerate, and there's the 1 electron in there. So if we just had the regular spherical situation, we'd have the electron here. However, we got octahedral, so that electron is stabilized by 0.4 delta oct. So we'd say that the crystal field stabilization energy, because the electron is here rather than there, is minus 0.4 delta oct. Let's put a second electron in. It's going to go there. So that's 2 in the T2G. And that compares to 2 in this barycenter situation. The stabilization is going to be 2 electrons stabilized by 0.4. So in other words, a total of minus 0.8. 3 electrons, minus 1.2, all 3 stabilized by minus 0.4. So first of all, make sure you've got the idea of what we're doing here. We're saying we're putting the electrons in the octahedral situation, and then we're comparing the energy to just the regular old degenerate situation. Okay, and right now we've put in 3 electrons, up to 3 electrons, all of which are stabilized by minus 0.4. So first one minus 0.4, second one minus 0.8, third one minus 1.2. Gets more fun when we get up to the D4 situation, because we can go high spin and low spin. Well, let's go with high spin first of all. And so the high spin, the electron is going to pop up into the EG, because the split between these 2 sets of orbitals, the delta octahedral, is not very big. Okay, so we got a weak field, right, to use the terminology from the last one. 4th electron, of course, just pops along into there. So now what we're doing is we're comparing a T2G3 EG1, so we got 3 stabilized, 1 destabilized, with this situation where all 4 are in their own separate little d orbitals. Okay, 3 stabilized minus 0.4 is minus 1.2. However, one of them's destabilized by 0.6, so the overall crystal field stabilized energy is minus 0.6. Throw in our D5. It's going to go in here again into the EG. We're in a high spin situation, so it's T2G3 EG5. All 5 electrons in the barycenter are, of course, in their own individual orbitals. Total CFSE, pause it and work it out. Hopefully you found it was 0, okay, because we got 3 at minus 0.4 is minus 1.2, 2 at 0.6 is plus 1.2, cancel each other out. So D5, remember, nice stable situation. Anyway, we can see the octahedral coordination doesn't actually do much for that high spin D5. High spin D6, that 6th electron pops into the T2G, so we're getting a pairing here. So it's T2G4 EG2. But of course, we're also going to be getting a pairing in the barycenter. So the fact that we got a pairing here doesn't actually hurt, because the barycenter would have the pairing anyway. So the stabilization is still going to be, we've got 4 here stabilized by minus 0.4. We got 2 destabilized by 0.6. Minus 1.6 plus 1.2, overall minus 0.4, and then go to the D7, and I'm going to speed up a little bit here. I'm going to have minus 0.8. Okay, Then after that, we can finish off D8. Looks like that. So we got 3 pairs, 6 electrons in the T2G and 2 electrons in the EG. Stabilization compared to here, minus 0.4 times 6 is 2.4, minus 2.4. We got 2 here at plus 0.6, that's 1.2. So the total stabilization minus 1.2 delta oct. Then go to the D9. Doesn't matter whether you're low spin or high spin, it's the same thing. You've got this T2G6, EG3, stabilization associated with that minus 0.6. Okay, so here's our high spin CFSE. Make sure you see where we get all of those from, and you can see that all except the D5, they all stabilize in the octahedron compared to where you've got just the spherical electron charge. But let's go back to the D3 situation and think now about the electron configuration and the CFSEs when we're dealing with low spin situations. Okay, so in other words, this is where this energy gap is really, really, really big. The delta oct is very large. So therefore, it's better for an electron to go here, even if it has to pair up, rather than pop up here. Okay. So this fourth electron for D4 pops in the T2G. So the D4 low spin electron configuration, 4 in the T2G, nothing in the EG. In the baryon center, however, D4 is still 1, 2, 3, 4, all separated out. So let's compare these. First of all, we got 4 electrons that are stabilized by minus 0.4. So we get minus 1.6 delta oct. But we have now here got paired electron, whereas we don't have that up here. And pairing is bad for 2 reasons. First of all, pairing means we lose the exchange energy. If you remember this from last semester, exchange energy is the stabilization when you can start switching over electrons. You can almost think of this in the entropy terms you've just been studying earlier in this semester, right? When we got 4 unpaired electrons, there are 6 possible swappings that we can do, right? 6 ways in which we can organize those. When we've only got 3, like pointing up here, right, then there's only 3 ways in which we can organize those. So we've lost some exchange energy by putting this 4th electron in a position where it can't exchange in the T2G. It could exchange up here in the baryon center situation. And of course, we've also got some electron repulsion going on. So this pairing energy is actually a destabilization, so we've got to incorporate that here. So the crystal field splitting for a low spin D4, minus 1.6 delta oct, which is of course wonderful, but plus this pairing energy. Okay. Move to D5, there's the 5th electron in, so T2G5. Compare this situation to the baryon center. Pause it and work it out yourself. We got 5 electrons stabilized by minus 0.4, so that's minus 2. But we've got 2 pairing here compared to no pairing in the baryon center, so that's plus 2p. D6 low spin, 6th one goes in there, so T2G6. But where does the 6th one go in the baryon center? And the answer is it pairs up. Okay, so now again, pause and tell me, excuse me, what this crystal field stabilization energy is going to be here when you got 6 electrons in the T2G and you can see the pairing. Well, 6 times minus 0.4 gives us minus 2.4 delta oct. How many pairings we got? Now some of you might have said, oh, it's plus 3p, but no, yes, we got 3 pairs here, but remember we're comparing it to the baryon center. There's a pair in the baryon center, so the pairing term here is still again plus 2p. D7, T2G6, EG1. Okay, 7th one's going to go in there, so we'd have 2 pairs here. I don't think I incorporated that in. No, 2 pairs going to be in the baryon center. Excuse me, there should be 1 there. We got 3 pairs in the T2G situation. We've got 6 electrons stabilized by 0.4, so that's minus 2.4. We got 1 destabilized by 0.6, 2.4, and 0.6 gives us minus 1.8. But while there's 3 pairs here, there are 2 pairs in the baryon center. Remember, that one's paired up as well for the 7th, so therefore there's only 1 pair in energy. And of course, D8 and D9, we don't distinguish between low spin and high spin. Okay, now compare the crystal field splittings here for our low spin versus high spin. And I hope you can see this little pattern. This is separated in the D4 minus 0.6 to minus 1.6, so there's a delta oct stabilization between the low spin and the high spin, right? The low spin is a delta oct more stable than the high spin is, but it's also a P less stable, okay? Go to the D5s, and the difference is in terms of delta oct is 2, more stable for the low spin, but the low spin is also destabilized by 2p. So you got difference of 1 delta oct and 1p, 2 delta oct and 2p. Again here, 0.4 to 2.4 is a 2 delta oct stabilization for the low spin, but you got 2p destabilizing it. And here there's a change of 1 delta oct or 1p. Okay, so essentially the differences between the low spin and the high spin come out to be a whole number of delta octs and the equivalent whole numbers of p's. So if delta oct is less than p, in other words, if it's easier to stick an electron up here than it is to pair up here, you'll get a high spin. If on the other hand, delta oct is greater than p, so this is a big one, right, a strong field situation, well then it's going to be harder to stick an electron in here to overcome the delta oct than it is to overcome the p, so you will get a low spin situation. So anyway, that was 11 minutes spent on one slide. I don't remember the last time that I did that, so I think it's time to do a little bit of thinking. First of all though, I'm going to save this. Okay, it was kind of excessive, wasn't it? But let's take what we did actually finishing the previous slideshow and then this one and look at a couple of things. So, cobalt with 6 waters. So Hexa aqua cobalt 3 cation is found to be low spin. What can you say about the cobalt electron configuration in, first of all, CO BP 3? Okay, well this is cobalt 3. BP is a bidentate nitrogen containing ligand, so we're dealing with cobalt 3 there. Okay, when we find things in the spectrochemical series, we find that the little chunk that has BP and water, BP is a pretty strong ligand, water is of course a medium type ligand, so BP is stronger than water is. Okay, this is cobalt 3, this is cobalt 3. We have a stronger field ligand in this one than in this one. So if the water was already low spin, that's saying that the water is acting as a strong field ligand in this complex, and seeing as how BP is stronger than water, this has got to be low spin as well. Okay, now COF6 3 minus, okay, is going to be CO3 again. You got 6 fluorides, each at -1, so that's -6. The whole thing's -3, so cobalt must be +3. Okay, but now we find fluoride in the spectrochemical series, and we find that it's a weaker one than water. Okay, so we know the water makes us low spin, so the water must be a strong enough field to make it low spin. The question is, what's the fluoride in this case? And the answer is you can't tell, right? Fluoride could quite easily also be low spin, because maybe the change between low and high spin comes down here for cobalt 3, or maybe the change from low spin to high spin is between the water and the fluoride, in which case the fluoride complex would be high spin, but you can't tell. Okay, now finally, COOH, there's waters, 6, 4+. Well, water is a neutral ligand, so if this whole thing is 4+, it must be cobalt 4. Now, if cobalt 3 with water is low spin, when you go to a higher oxidation state, you're more likely to be low spin. The higher oxidation state's a stronger field, so therefore you can immediately say that will be low spin. Cool? Now let's stay on cobalt. Oh, sorry, let's stay with 6 waters, but let's move to chromium. Chromium 2+, so this is chromium 2, okay, for which spectroscopic measurements, so delta oct is 170 and P is 245, both of those in kilojoules per mole. Will this complex be high or low spin? Okay, well, chromium 2+, that's a fairly low oxidation state, so that could be high or low. Water is a medium range ligand, so that could be high or low. So we couldn't actually really tell ordinarily, but what we can do is we can look at these actual values and think about it. Okay, we got chromium 2, which is D4, right? There's chromium 2, right? We're going to have 2s electrons will already have gone. So, or 2 electrons already gone, one from the s, one from the d. So chromium 2 plus is D4, okay? If we look at the high spin situation, we find that the stabilization energy is minus 0.6 delta oct. That was from the previous slide, okay? On the other hand, low spin for D4 is minus 1.6 delta oct stabilization, but P's worth of destabilization. And we know delta oct and we know P. So for the high spin, 0.6 of 170 is equal to 102. So the high spin is stabilized compared to the, I want to say Barrymore. I'm gone a complete blank. Anyway, to the one where they're all degenerate is minus 102 kilojoules per mole. For the low spin, we got 1.6 times 170 is minus 272, but P, that destabilization, 245. So the low spin here is only stabilized by minus 27 kilojoules per mole. Right? Delta oct is fairly small. It's small compared to P. If delta oct is small compared to P, then we expect the high spin to be more stable. Okay, so that was just a quick little illustration of how those things work. Let's have a quick comparison between octahedral and tetrahedral in terms of trying to use our crystal field theory arguments. Okay, the most D3 complex is octahedral. Both octahedral and tetrahedral geometries observed for high spin D7 rationalize these statements in terms of crystal field splitting energy arguments. Well, we can go straight from our octahedral chart for the D3 and the high spin D7. Okay, now let's think about tetrahedral. Okay, there's the splittings associated with the tetrahedra, stabilization of 2 orbitals by 0.6, destabilization of 3 by 0.4. If we think about D3, 1, 2, 3, up there in the tetrahedral, which we're going to say is a high spin situation. Okay, so that's 0.8. Negative 0.8 stabilization. We get that because we got 2 here at negative 0.6, 1 here at plus 0.4. Okay. If we think about high spin D7, 1, 2, 3, 4, 5, 6, 7. Okay. Stabilization there, we got 4 times negative 0.6, that's negative 2.4. We got 3 at plus 0.4, so that's plus 1.2, minus 2.4, plus 1.2, overall negative 1.2 delta tet. Okay, so that's the octahedral and the tetrahedral. Remembering we're saying the tetrahedral are pretty much always going to be high spin. Okay. Now, the relationship between these, delta tet and delta oct, is that delta tet is 4/9 delta oct. So if we've got here minus 0.8 delta tet, that corresponds to minus 0.36 delta oct. In other words, just take 8 and multiply it by 4/9. Conversely, if we've got minus 1.2, multiply that by 4/9, and we get minus 0.53 delta oct. Okay. Not quite sure what happened with my clicking there, but anyway, differences here for the D3 octahedral is minus 1.2 delta oct stabilization. Tetrahedral is only minus 0.36 delta oct. There's a big energy difference there, regardless of the size of delta oct. So unless delta oct is absolutely teeny, right, that significant energy difference is probably going to mean octahedral rather than tetrahedral. Conversely, when you get up to the high spin D7, the differences between them is just about 0.27 delta oct. So if delta oct is small, well then this difference between them is going to be relatively small. And so tetrahedral will be much more likely than it was up here. Okay, so we'd expect to see, because the great stabilization here for the octahedral compared to the tetrahedral, D3 will go octahedraly. Down here for the high spin D7, much smaller difference between the octahedral and the tetrahedral, so you could expect to see both. Of course, another argument for it is that D3, you don't have much electron density, so you can accommodate 6 ligands. On the other hand, D7, only 4 ligands might be preferable.